Good evening to all of you, and once again I welcome you, all of you. So this is Narayan Sharma, Government First Aid College, Vartur, Bangalore 87. I am continuing my discussion on quantum mechanics part 2. So that is there for BSc 6th semester physics course for Bangalore University, Bangalore North University, and Bangalore Central University. So the paper that this particular topic belongs is paper 8. So this is my fourth session, and in this fourth session, I would like to talk about the postulates of quantum mechanics. So in this particular session, I would like to discuss exclusively on postulate of quantum mechanics. Just like any other theory, each and every theory in physics has a set of postulates. For example, if you consider special theory of relativity, the special theory of relativity is actually based on two important postulates, which I'm not going to discuss here. Anyhow, similar to special theory of relativity, even our quantum mechanics is actually has a set of postulates. So therefore, in this particular session, I would like to discuss a little bit in detail about the postulates of quantum mechanics. Logically speaking, this should have been the first topic. Anyhow, we're not discussing quantum mechanics in a formal way. So right now in this particular session, so we're discussing about the postulates. Before we discuss the postulates, let me summarize what are the objectives of this particular session. So definitely the very first objective is to understand the postulates of quantum mechanics. So as I have mentioned, so all just like any other theory of physics, even our quantum mechanics is based on certain set of postulates. Here in this particular session, I would like to mention 5 different postulates of quantum mechanics. So therefore, our first objective is to understand the postulates of quantum mechanics. Now, while discussing the postulates, we will come to know about several other things. So, for example, so we introduce observables and operators. So, in one of the postulate of quantum mechanics, we talk about observables and operators. So, therefore, we shall also try to understand the relationship between observables and operators in quantum mechanics. In quantum mechanics, each and every observable, physical observable or dynamical variable, what we call it as, is represented by an operator, quantum mechanical operator. So therefore, that is what the thing that we want to understand. So therefore, the second objective is to understand the relationship between observable and operators. Then we also try to understand what is an eigenvalue equation of an operator. We speak of eigenvalue equation of a particular physical observable or a dynamical variable. What is that eigenvalue equation? What are the eigenvalues? What are the eigenfunctions? So these are the things we want to understand. So therefore, we also try to understand about this eigenvalue equation and their solutions. And at last, we would like to understand another concept called expectation value of an observable. We cannot find out the value of a particular physical quantity accurately, but instead we define something like an average value. That average value is given the name expectation value. This expectation value can be defined for each and every observable, physical observable. So therefore, we shall also try to understand the expectation value of an observable in quantum mechanics. So therefore, so by trying to understanding the postulates of quantum mechanics, we shall also try to understand several other things like observables, operators, eigenvalue equation, and expectation value. Let us do it one by one. Let us first discuss the postulates of quantum mechanics. I have already mentioned, just like any other physics theory, even our quantum mechanics is also based on certain set of propositions, certain set of postulates. And these postulates of quantum mechanics are verified by experimental observations. So postulates are the things which we cannot prove. Okay, so therefore, even in the case of quantum mechanics, these postulates cannot be proved using any other logic. But the only thing is these postulates are based on experimental observations. Or also I can say that these postulates have been verified by doing several set of experiments. So therefore, I can say that, so the postulates that we are discussing in quantum mechanics, they are based on a wide range of experimental observations. So based on the experimental observations, these postulates have been postulated, or these postulates have been given. Let us discuss one by one. The very first one talks about, so the existence of wave function. So the first postulate says the state of a physical system at each time t, so is represented by a wave function psi, and the wave function psi contains all the needed information about the system. When we talk of a particular physical system, for each and every physical system, it is possible to find out through mathematical equations called as Schrodinger equations. We shall do it, all these things will in detail a little later. So therefore, I can conclude that for each and every physical system, it is possible to find out a wave function psi. And the wave function psi actually contains all the information about that particular system. So therefore, if you want to find out any particular information, any set of information about a given system, so one has to do is to find out the wave function of that particular system, and then so one has to analyze the wave function properly in order to get the information. So something like we can say that, so wave function psi is something like a tool which encodes all the information regarding the system, the given physical system. So this is what the first postulate. The first postulate talks about, so the existence of a wave function for a given physical system, and it also says that, so using that value of wave function psi for that given system, it is possible to find out all necessary information about the system. So this is the first postulate. Now, so let us go to the second postulate. So for each and every physical system, there are several physical quantities associated. So these physical quantities so can be measured. So therefore, these physical quantities are also called as observables or dynamical variables. So the physical quantities associated with a given system. So please remember, physical quantities in the sense they can be measured. By doing certain set of experiments, it is always possible to find out the associated physical quantities with the system. So these physical systems associated with the physical given system, so physical quantities associated with a given system, they are actually called observables or dynamical variables. So from here onwards, I am going to use the word observable. An observable is a physical quantity associated with a system which can be observed. Observed in the sense it can be measured, so using some experimental techniques. So according to quantum mechanics, each and every observable associated with the system is actually can be represented with the help of a linear Hermitian operator. So let us call one of the observable as B. So there can be several observables associated with the system. So let us take one such observable. That one such observable, let us denote it by the letter capital B. And according to this particular postulate, so all observables, they can be represented by an operator. And these operators are not ordinary mathematical operators. Basically, they are linear Hermitian operators. So we are going to discuss about this linear Hermitian operator. What is the Hermitian operator? I'm going to explain a little later. But anyhow, so according to this particular postulate, for each and every observable B, there corresponds a linear Hermitian operator, and that is actually denoted by B cap. We are using this symbol exclusively in our discussion. If you want to take an observable as C, then the respective Hermitian operator is represented by C cap. If you take an observable, let us say A, then the respective operator is denoted by A cap. Since I have written observable symbol as B, so therefore the respective Hermitian operator is written as B cap. So therefore, for each and every observable, there corresponds a linear Hermitian operator, so represented by B cap. The letter B is the letter used to denote that observable. That cap actually denotes the operator form, Hermitian operator form of the respective observable. So this is what the second postulate. Now let us try to understand within this postulate itself, what is a quantum mechanical operator and an observable. I mean, the relationship between quantum mechanical operator and observable. So an operator in quantum mechanics is a mathematical rule that when applied to a wave function yields the same wave function multiplied with a constant. Here I have tried to give an explanation for operator within the realm of quantum mechanics. So in quantum mechanics, an operator means basically it is a mathematical operator which always operates on a wave function of the given physical system. And when it operates on the wave function of the physical system, it yields the same wave function but multiplied with some constant. So these constant are constants, they are called eigenvalues. I'm going to explain this little later. And since we are talking of Hermitian operators in quantum mechanics, so all physical observables in quantum mechanics are represented only by Hermitian operators. So therefore, these Hermitian operators have eigenvalues which are always real. So therefore, so that's what I have written here. So an operator in quantum mechanics is a mathematical rule that when applied to a wave function yields the same wave function multiplied with a constant, and that constant or set of constants are called eigenvalue or eigenvalues, and these eigenvalues are always real, because here we are discussing only Hermitian operators in quantum mechanics, because all other operators have complex numbers as their eigenvalues. Such complex numbers as eigenvalues are not allowed in quantum mechanics. Only real values are allowed here. So therefore, an operator in quantum mechanics, a Hermitian operator in quantum mechanics, is a one which operates on a given wave function of the system, and after operating on that given wave function, it yields the same wave function and it leaves another constant or a set of constants. These set of constants are all real, and these constants are actually called eigenvalues. So that is what the definition of your operator. And here an observable is a dynamic variable that can be experimentally measured. I have already explained this little earlier. So an observable is a physical quantity associated with a physical system, and therefore, so an observable can be observed in the sense not directly through the eyes. So it may not be directly through the eyes. It can also be detected through with the help of certain instruments. So in that sense, we call it an as observable. So the dynamics, I have mentioned something here, some of the observables here, the dynamic variables encountered most in the classical mechanics. For example, if we deal with the classical mechanics and the Newtonian mechanics, so the very famous dynamical variables are observables are position, linear momentum, angular momentum, kinetic energy, total energy, and so on. So therefore, these quantities are also called observables. Position is an observable, linear momentum of a particle is an observable, angular momentum of a system is an observable, total energy of a system is an observable, and so on. So therefore, according to this second postulate, please remember we are still in the second postulate, we have not yet moved to the third one. So therefore, according to the second postulate, each and every observable may be position observable, linear momentum observable, angular momentum, or energy, or something else. There can be several other observables. All these observables are actually replaced by a Hermitian operator in quantum mechanics. So therefore, according to the second postulate, all physical observables associated with a system are represented by a Hermitian operator in quantum mechanics. Okay, I have been telling this Hermitian operator repeatedly. So anyhow, I'm not going to discuss all these mathematical properties of a Hermitian operator here, because all those things are beyond the scope of this particular session. So therefore, I would like to give one simple definition for Hermitian operator. A Hermitian operator is a one whose eigenvalues are real. I just mentioned previously that when an operator operates on a wave function, it yields the same wave function along with a constant or constants. These constant or constants are called eigenvalues. So therefore, if you operate a Hermitian operator on a particular function, then whatever the constant that we are going to get, those constants are all real. And such a thing is possible only if the operator is Hermitian operator. So therefore, all physical observable, so in our physical system, they should be represented by Hermitian operators only, not any other non-Hermitian operator, because non-Hermitian operators would give complex eigenvalues which are not possible in our physics. So therefore, all physical observables are represented by Hermitian operators. A Hermitian operator is a one, so whose eigenvalues are real. So, okay, so here I have mentioned some of the physical observables and their Hermitian operators. I have given a table here. So as per this table, I have tried to mention some of the physical observables and their Hermitian operator representatives. So the first one is the position. The first observable is the position vector in the three-dimensional case. The position vector in the three-dimensional case is written as vector R, and the respective Hermitian operator is written by capital vector R cap. So I have written a cap here. You can see in the study material, although it is not clearly visible here. So therefore, for the position vector, which is represented by the symbol vector R, the respective operator, Hermitian operator, is written as vector R cap. Now we have the second quantity, linear momentum. Linear momentum in the three-dimensional case is written by vector P, and the vector P in the three-dimensional case, the operator form is minus IH cross del, where del is a mathematical operator, which is nothing but I cap into dou by dou x plus j cap into dou by dou y plus k cap into dou by dou z. That is what the del operator. So therefore, the linear momentum is represented by the operator, quantum mechanical operator, Hermitian operator, which is nothing but minus IH cross into del. Now we have classically, we have kinetic energy, another quantity, another observable, and according to classical physics, the kinetic energy is given by p square by 2m, square of the linear momentum divided by 2 times m, where m is mass of the particle of the given system. So therefore, this vector operator is represented by, we can substitute vector p or vector p into p, vector p into vector p. If we take the scalar product, then we get p square. And if we do that simple thing, then we are going to get the operator representative for vector t cap. So it is given by minus h cross square divided by 2m into del square. This is the term which actually comes in Schrodinger's equation that we have already discussed in the previous sessions. Now the total energy of the system is also another physical observable. The total energy of the system is nothing but the sum of the kinetic energy and potential energy, p square by 2m plus v of RT. So therefore, the respective operator is called Hermitian operator. The operator of the total energy of the system is called Hamiltonian operator. The Hamiltonian operator of the total energy is written as h cap, and it is given by minus h cross square by 2m into del square plus p cap of r vector r cap of comma t. So this is what, the vector operator representation of the Hamiltonian operator or the total energy operator in quantum mechanics. And I have also mentioned one more thing. So one more observable, it is angular momentum. Classically, angular momentum is defined by the cross product of position vector and the linear momentum r cross free. So therefore, if we use the same symbol, the vector representative of your operator representative of the angular momentum is given by vector L cap, that is equal to minus IH cross r, IH cross vector r cap. This is the vector symbol for position vector, and we have the operator form for, your momentum is IH cross into del, and IH cross I have already taken it outside. So therefore, the operator form of angular momentum becomes minus IH cross vector r cap into del. So this is what, the operator of Hermitian operator of angular momentum. Now let us proceed. Let us come back to our postulates. So we have discussed the second postulate in detail, relationship between observables and their operators, and some of the examples for the operators. Now let us go to the next third postulate. The third postulate speaks of in this manner, the measurement of an observable. Let us assume we are assuming an observable. Observable is represented by P, and we are making an observation on the measure on the observable P. This is represented by the action of the Hermitian operator B on the wave function psi of the system. The only possible result of such a measurement is one of the eigenvalues Bn, which are all real, because the operator is a Hermitian operator of the operator B. So thus we have the third postulate speaks about measurement. Suppose, for a given physical system, there is an observable, call that observable as B, and its respective representation, its respective operator is B cap, and we are trying to do certain measurement on the physical system. We want to measure the observable P, and whenever we try to measure the physical observable B, then we are going to measure one of the eigenvalues of the operator vector B. So therefore, so this is what the third postulate, and we are going to end up with an equation. That equation is what we call it as eigenvalue equation. And the eigenvalue equation is mathematically given in this fashion. So operator B acting on the wave function psi of the system gives the same wave function psi. Apart from that wave function, we also end up with some multiplication factor or factors. These factors are written by Bn, and this Bn is what we call it as eigenvalues. And these eigenvalues are all associated with the operator B or the observable B. So therefore, these are all called eigenvalues of vector B. And this particular equation is what we call it as eigenvalue equation of the operator B. The thing is, so although we have written this one mathematically, so there is a lot of physical significance, and the physical significance is that whenever we make certain measurement on the given physical system, and while doing the measurement, we are trying to measure a physical quantity B, then what are the values that we are going to measure? So for the particular physical observable B, they are nothing but the eigenvalues of B or eigenvalues of the Hermitian operator B cap. So therefore, so this is what one of the fundamental foundation principle of your quantum mechanics, and it talks about eigenvalue equation. And whenever we try to do the measurement, we always end up with eigenvalues. Okay, there is one more important thing. If the result of such a measurement of BA on the state psi of the system is Bn, then the state of the system immediately after the measurement changes the respective eigenstate. Whenever we try to do certain measurement in a physical system, we are trying to observe a physical observable, then the state of the system changes, and the state of the physical system before measurement, if it is psi, then state of the system after the measurement, whose eigenvalue is Bn, and one of the eigenvalue of Bn. Corresponding to the respective eigenvalue, we have set of eigenfunctions. So therefore, the state of the system jumps to the respective eigenfunction corresponding to the measured eigenvalue. So state of the system would be in one particular state, and we are trying to measure some particular physical quantity. And if we measure the physical quantity, we measure any one of the eigenvalue associated with that particular operator, and the state of the system doesn't remain to be in the same state even after the measurement also. And after the measurement, the state of the system actually jumps to the respective eigenfunction of the whatever the measured eigenvalue. So this is what the third postulate. Now let us move on to the fourth postulate. The fourth postulate talks about average of a large number of independent measurements of an observable is called expectation value. So whatever the overall value of a physical observable that we try to measure for a given physical system is something like average of large set of eigenvalues. And this average of large set of eigenvalues or the average of large set of these measured values is what we call it as expectation value. So therefore, the fourth postulate talks about expectation value. So because of uncertainty principle, it is not possible to measure absolute value of the physical quantity associated with the system. But if we do make large number of measurements of the observable, then we measure something like an average value of that particular observable. And that average value of that particular observable is what we call as expectation value. So therefore, we always speak of the expectation value of an observable, expectation value of an operator. Okay, let us try to understand this one mathematically a little bit. If the measurement is made on observable B, let us call it observable as B. So the respective operator is B cap. Then the expectation value of B within this bracket is given by expectation value of B is given by integral over the entire region. So of the physical system, psi star, where psi star is the complex conjugate of the wave function psi of B cap into psi into dV divided by psi star into psi into dV. This is what the mathematical explanation, mathematical definition of your expectation value of the observable B. So numerator can be written as it is psi star B cap psi into dV, whereas the denominator is nothing but the absolute square of the absolute value of the wave function. So please you should keep in mind that the integration should be carried over the entire region. And we talked about normalization functions in the previous session. So therefore, the wave function is normalized. So the term in the denominator becomes equal to 1. So therefore, in the respective case, we can write the expectation value as integral of psi star b cap psi into db, where b cap is the Hermitian operator of the observable b, whose expectation value is b, is given by this particular equation only for a normalized wave function. If it is not normalized, we have to use basic definition in this fashion. But if it is normalized, we can go and use this. Okay. So therefore, we always speak of the expectation values. Like in classical mechanics, it is not always possible to find out the exact value of the physical observable. That is not possible here. Whereas it is always possible to measure an average of large number of measurements, and that is what we call it as expectation value. And expression for the expectation value is given by this particular expression. So we have completed 4 postulates. There is one more last postulate that let us discuss. And I have given some expectation values of some operators. For example, expectation value of linear momentum is given by, expectation value of linear momentum is equal to psi star integral psi star vector p psi dv. So vector p operator form is minus I h into del. Minus I h cross term can be taken outside. So therefore it becomes minus I h cross into integral of psi star del of psi into dv. And here we are assuming that the wave function psi is normalized. Similarly, expectation value of the total energy is given by, so expectation value of E is equal to integral psi star h cap psi into dv, where h cap is called Hamiltonian operator. The operator of the total energy is what we call it as Hamiltonian operator. So the Hamiltonian operator is actually represented by IH cross into dou by dou t. So it is possible to take IH cross outside. So therefore we can write IH cross into integral psi star dou psi by dou t of t. So if you perform this entire integration, we are going to end up with the expectation value of the energy. So these are the 2 examples for the method of calculation of expectation values of 2 different quantities, linear momentum and total energy. Let us move on to the last topic. So the time evolution, the last topic or the last postulate. The time evolution of the wave function psi of a system is governed by the time independent Schrodinger equation. And time dependent Schrodinger equation is actually given by minus IH cross into dou psi by dou t is equal to h cap into psi, where h cap is nothing but the Hamiltonian operator corresponding to the total energy. So if you consider any physical system, so the physical system, even if you don't disturb externally, it keeps on evolving. And this evolution of the system changes the value of the wave function associated with the system. And so one can find out the value of the wave function at a later instant of time if one knows the value of the wave function at some initial condition. Then this evolution is actually based on the Schrodinger's time-dependent equation. And according to this, the evolution happens such that it always follows the equation IH cross dou psi by dou t is equal to h cap into psi, where h cap is the Hamiltonian operator of the total energy of the system. So I would like to conclude. So there are 5 different postulates of quantum mechanics. The first one talks about the physical system wave function, which gives all the complete information. The second one says that each and every physical observable is represented by a Hermitian operator. So the third one actually talks about eigenvalue equation and what is going to happen if we do the measurement on a particular observable. So the fourth one talks about expectation value, and the fifth postulate actually talks about the time evolution of the system, or the time evolution of wave function of a physical system is actually governed by Schrodinger's time dependent equation. So I'm going to end this session right now. So I will continue in my next session.